All right, we're at lecture 16b now. So lecture 16a was a smorgasbord of topics related to tangent lines, essentially. And lecture B, we're going back to the infinitesimals. The idea of doing calculus without limits. I call it calculus sans limits. Sans is just another word for without. It's kind of fun in a way, I think. I think it's probably the most fun topic we've done so far. But it is kind of weird and it's kind of hard to get used to, and it's also a situation where you're never quite sure if you're doing it the right way. And so I have to teach you the right way. I would not necessarily be able to be expecting you to do what I'm about to do with sine and cosine. Okay? Not without some guidance, because it is tricky. So that's going to be our example here. Y equals f of x equals sine of x. This is the example I did start very briefly at the end of class on Wednesday. Well, it was kind of rushed. Let's do it more carefully now. What do we want to do? We want to find the derivative, dy dx. That's the goal. We first find this thing called an infinitesimal. What is the infinitesimal change in the output given an infinitesimal change in the input? And what is an infinitesimal? It's something in our imaginations. A nudge, a change so small that it's essentially smaller than any positive real number. Which, if you think about it, doesn't make any sense. How can there be a number smaller, a positive number smaller than any other positive number? Because you can always divide a positive number by 2 and get a smaller positive number, for example. You can square a number between 0 and 1 and always get a number closer to 0. So this idea of infinitesimals is an imagination kind of thing, but it's a useful, convenient fiction is what I call it. And again, if you want to get good at using calculus outside of math, physics, chemistry, biology, engineering, you want to learn to think this way. And this is the way those teachers think, typically. They don't typically think about limits. They don't care too much about epsilon delta proofs. Okay, it's mostly only the mathematicians that care about that. You may see it again in your future, but for the most part, this is a more important kind of skill to have. Think about it in terms of infinitesimals. Notation-wise, this is also called df. And that's what in the 3 blue 1 brown videos, what he typically calls it is df. Here I'm thinking of it as an infinitesimal change in the dependent variable, y. Here I'm thinking of it as an infinitesimal change in the function output. F is the name of the function, df is the infinitesimal change in its output. And here's what it initially equals for the sine function. Then the question is, what do you do with this? How can you make any progress? And with trig functions, one of the most common ways to make progress is to look up a trigonometric identity and use it and hope that it is going to be helpful. Cross your fingers. Pray, okay? Oftentimes, they are helpful, though you've got to have enough practice to know what to do. We can use this identity in particular. What's the sign of a sum of 2 angles? Called the angle sum trig identity. Are we thinking of these inputs as being angles? Well, we could. We don't have to, but we could. Anyway, you might remember from pre-calc, sine of A plus B is sine of A cosine of B plus cosine of A sine of B. You can check that with numbers. You can check it with graphs. You can also do a more general derivation with a picture based on the unit circle set. It's a bit tricky though. For the moment, you're just trusting this. You can look it up, okay? There's a Wikipedia page about trigonometric identities. It's got like hundreds of identities. This is one of the more important ones, actually. Use it with A equal to, we're going to use it for this thing here. Use it for that thing with A equal to x and B equal to dx. What do you get? Get that. right? This thing here plus this thing here is the same as sine of x plus dx. I use this identity. I replaced a with x and I replaced b with dx. Then don't forget to subtract sine of x right there. Again, this is not in your book, but I think it's definitely worth teaching. Okay? Because I'm thinking about the fact that most of you are not math majors. Most of you are science and engineering majors, maybe business majors. This kind of mode of thinking is more useful for you. That does include business majors, actually, when you're thinking about more abstract economics, for example. Here's the trickiest part, the extra tricky part in this case. Since cosine of a is approximately 1 when a is approximately 0, write cosine of dx actually equals 1. And since sine of a is approximately a when a is approximately 0, write sine of dx equals dx. Okay? That's the kind of thing that you wouldn't have known to do without me telling you. But it does make sense. If you get your calculator out, I would recommend doing that. Make sure it's in radian mode. And calculate, for example, cosine of 0.01 when you're in radian mode. I'm doing it right now. I get 0.99995000004, and there would be more decimal places that I'm not including. It's going to be an irrational number, so they definitely go on without a repeating pattern. Try cosine of 0.001. You're going to get 0.9999995, and for some reason my calculator is rounding it just that far. It does not equal that exactly. I'm sure it's irrational, but my calculator is stopping the rounding right there. Let's try one more. Cosine 0.0001. I get 0.999999995. You know, this is only 10 to the negative what? 1, 2, 3, 4. Imagine finding cosine of 10 to the negative million power. There'd be a lot of 9s in there. It would not be 0.9 repeating because that actually equals 1. You may have heard, and it's true. 0.9 repeating does equal 1. It would not equal that. It would not equal 1 exactly, but it would be so close. I'm sure there'd be probably billions or trillions or quadrillions of 9s or something like that before you reach the first thing that was not a 9. Maybe even more. Probably even more. Maybe a Google 9s. Maybe even more before you reach the first number that's not a 9. dx is infinitesimally small. So close to 0 that's smaller than any positive real number, at least in our imaginations. Let's effectively say the cosine of dx equals 1. No approximation symbol there. Let's just go ahead and say it equals 1. What about sines of these things? Sine of 0.01 is 0.009999833. Sine of 0.001 is 0.00999999833. Sine of 0.0001 is 0.0099999, count my number of 9s here, 9983. All of these numbers are pretty close to 0.01. The same as the input. Oops, excuse me, sorry. got to change the number of zeros. Oh, and I'm doing it wrong. This one has 3 zeros in it. This one has 4 zeros. Sine of A, when A is really close to 0, is definitely very close to A itself when you use gradients. So let's just say sine of dx is dx. Make those replacements then. Replace cosine of dx with 1 to just get sine of x times 1. Replace sine of dx over there with dx. So instead of cosine x times sine dx, you get cosine of x times dx. Don't forget to subtract the sine x on the far right. And then the sines cancel, you're left with cosine of x dx. Now divide both sides by dx. The derivative of sine of x is cosine of x. This is not rigorous math. This is intuitive math. A mathematician would say this is not valid, at least if you don't use non-standard analysis. Hardly any mathematician I know uses non-standard analysis. Some do, but not many. It's really hard. That's the one where I looked at the book and I put it back on the shelf. Even me, I put it back on the shelf. It was like just too hard. And just, this is just more fun anyway. Why make it rigorous? It's so much fun. Why ruin it with rigor? Let's do it for cosine. We need another trigonometric identity, this one. Cosine of a sum. Cosine of A plus B equals cosine of A times cosine of B minus sine A times sine B. That minus is there. And again, you're trusting me on this. You might wonder, why is that true? Well, there are derivations online. You can look them up if you're really interested. It's not a super easy derivation. But it is a pretty fundamental trigonometric identity. So go ahead and make the replacement again. Use this identity with x equal being A being replaced by x and B being replaced by dx. And you get this. Don't forget the minus cosine at the end. Do the same thing as before now. Replace cosine of dx with 1 and sine of dx with dx. Same thing as before. This is the exact same thing as the previous slide. Then you get the cosine of x is canceling, and you're left with negative sine x dx, and so that means the derivative of cosine of x is negative sine of x. When x is in radians. These approximations that we use here only work the way they do when the input is in radians, not degrees. That's why radians is important, why it's special. Just like E is special because it makes derivatives simple, so radians is special because it makes derivatives simpler. Okay, and again, I wouldn't expect you to be able to derive this completely from scratch. I'm teaching how to derive it and how to think about it. And it is a useful skill. If I put this on the exam, probably I'd give you guidance. Okay? Maybe I'd remind you of what the trigonometric identity is. Maybe I'd remind you of these things. Replace cos dx with 1 and sine dx with dx. And then if I did that, if I told you those things, it would be a pretty easy thing to finish it. I don't know. I don't know if it's worth putting on the exam like that. Probably it's worth asking you more like, do this with y equals x squared, or y equals x cubed, or y equals x to the fourth. That's probably more worthwhile. In those examples, we were sort of ignoring the dx squared, the dx cubed, the dx to the fourth, because they were unspeakably small. It's my terminology. dx is infinitesimally small. I said dx squared was unspeakably small, just to try to be extreme in the way I described it. So we can ignore it, treat it like it's 0. This infinitesimal thing is useful for other things, like deriving the product rule. I think for the sake of time, I'm going to not go through the details here. It's on the slide. I would highly encourage you to think about it. I am using df and dg instead of dy because there are two functions that are being multiplied, so it's more convenient to use the df and dg infinitesimals rather than say dy. And in Three Blue One Brown's video by Grant Sanderson, that's the kind of notation he uses. I'm going to skip this slide, okay? It's there for you, you can look at it. I even have a lull in there. I didn't know what that meant even like 7 years ago. But then my son started texting it to me. I'm like, oh, lots of love, thanks. That's what I thought it meant, lots of love. I suppose it could mean that, but. Anyway, here is the product rule. That is worth writing down. H prime of x, when h of x is the product of two functions, f of x times g of x, then h prime, the derivative of that product, is the first function times the derivative of the second function, plus the second function times the derivative of the first function. And because addition is commutative, you can do it the other way around as well. And I also, I guess, have switched around these two things. Multiplication is commutative too. Both of those are okay. That's how to take the derivative of a product. Let's apply it now. The product rule in action. This is our last slide for the day. It's got some important things on it. I'm not going to do all three examples that I have on here. Let's do the second example. Well, maybe I should do the third example first. Take the derivative with respect to x of x times square root of x. This can be done in two ways. What's the way to do it with the product rule? Well, first of all, realize the square root of x is x to the 1/2. We do have the product of two functions here. That product rule that you see over on the other side of the board there says, I use the first form, this is the f of x, this is the g of x. It's the first function, f of x, which is x, times the derivative with respect to x of the second function, x to the 1/2, plus the second function, x to the 1/2, times the derivative with respect to x to the first function. That's what that says. Get that in your brain. That's what it said. Come back over here. This says h prime is the first function times the derivative of the second function, plus the second function times the derivative of the first. And switch the order there. That's what I'm doing. To figure out these other derivatives, I need the power rule. Bring down that 1/2, like that. Subtract 1 from the exponent. 1/2 minus 1 is negative 1/2. The derivative of x is just 1. Simplify. This is 1/2 x to the 1/2 plus x to the 1/2, which is 3/2 x to the 1/2. The other way this could have been done is without the product rule. I could have written this just as a power to begin with, x to the 3/2, and used the power rule right away, and I would have more quickly gotten to the exact same answer. That's the better way to go in this example. Write it that way, just use the power rule without using the product. But it's nice to see that they give you the same answer. All right, let's do number 2.
if you have x times 1/2 to x times 1/2 times x to the negative 1/2, shouldn't the x to be in the denominator?
Are you wondering about this?
Yeah, and then going to the next equation, no, down.
No?
Yeah.
Yeah. This 1/2 is being multiplied. I can put it in front like that. And then I'm adding the exponents here. 1 minus a half is a half.
Yeah.
Let's look at example 2. F of x equals x squared e to the x. And let's do the other thing that says to do there on the PowerPoint. If you want to look quick at the PowerPoint too here with the camera. I'm saying also figure out where for this function is the tangent line horizontal. Where is the function increasing and decreasing, and where is it concave up and concave down? The derivatives will tell me these things, the first and second derivative. It is a product. I need the product rule. Well, I guess I better not call that f of x there. This is g of x and this is h of x. So I'm switching around my notation. Okay? Well, it's the same principle. This is the product of two functions. The product rule says it's the first function times the derivative of the second function plus the second function times the derivative of the first function. That's what it says. Get that in your mind. The first function is x squared. The derivative of the second, the derivative of e to the x is e to the x. H of x is also equal to e to the x. G prime is 2x. That can be rewritten as x e to the x times in parentheses x plus 2. A factored form of that second derivative. And that's a useful thing to do because it's more easy to see where it's equal to 0. And therefore, when the original function has a horizontal tangent. If I set this equal to 0 and solve for x, I get two solutions. 0 and negative 2. Those are where the tangent line is horizontal. I'm not going to write that down. You may want to write it down. When x is 0 and negative 2, that's when the tangent line is horizontal. Where is the function increasing and where is it decreasing? I'm just going to tell you what the graph looks like here. It looks something like this. And this is negative 2, and this is 0 here. You can check that with your calculator. So you can see from the picture that f is increasing when x is less than negative 2, the graph is going up. It's also increasing when x is greater than 0. You can check this derivative is positive for those values of x. F prime is positive in here, it's positive over here. It's negative when you're between negative 2 and 0. The product is negative. E to the x itself is positive, but when x is between 0 and negative 2, that's negative and this is positive. You got a product of two positives with a negative for the derivative will be negative. F is decreasing. Let's quickly take the second derivative as well. Or should we do one different thing here? I got 4 or 5 minutes. Let's take the second derivative. Is it better to use this formula or this formula? Probably this one, plus use linearity. F double prime of x, first take the derivative of this with the product rule. Hey, that's the exact same function as what we started with. Its derivative will be this whole thing. Cool. You follow me? I'm wanting to take the derivative of this sum here to get the second derivative of the original function. But this piece of the sum is the original function. So the derivative of this piece is going to be the same as what I have here. But I'm not done. I also need to differentiate this. I need the product rule for that as well. The first function, e to the x, times the derivative of the second. The derivative of 2x is 2. Plus the second function times the derivative of the first. These two things can combine to 4x e to the x And then once again, you can factor out an e to the x. And you can't factor out an x this time. What you're left with after you factor out an e to the x is x squared plus 4x plus 2, it looks like. The graph is going to change concavity when this equals 0. It's called an inflection point. Okay, is this factorable? No, not so easily. I think the roots are going to be irrational numbers. We can use the quadratic formula. 7 equal to 0, and solve for x with the quadratic formula. Square root of 8 is 2 square root of 2. These two cancel. Negative 2 plus or minus square root of 2. Square root of 2 is about 1.4. So these are about negative 3.4 and negative 0.6. Right about here and here, the graph changes concavity. You can see from the picture that you can reproduce on your calculator. It's concave up over here, concave down in here, and concave up over here. F double prime will be positive over here, negative in here, and positive over here. And you can check that. I know I'm going quick. One more thing I want to show you, and this will help you with the last graded problem for Monday. If Q is the quantity sold of an item at a price P, you should know from basic economics that Q depends on P. Demand depends on the price. Q is the demand. P is the price. So your problem is about skateboards. You're wondering, should I raise the price of my product, my skateboards for your home product? Think about it in terms of revenue. How much money is coming in? Revenue is P times Q. Price per item times number of items sold. Differentiate this with respect to P and see if it's positive or negative. To see whether you should increase the price or decrease the price to either make more revenue or make less revenue. You don't want to make less, you want to make more, right? You're hoping the derivative of this with respect to P is positive. The answer is not Q. The derivative of this with respect to P is not equal to Q, because Q is not constant. It depends on P. Revenue is really this function of P, P times F of P. To differentiate it, you need the product with it. What is the RDP? The first function is P. The derivative of the second function is F prime of P, plus the derivative of the first function, 1 times the second function. This is the derivative of the revenue with respect to price. In terms of the demand function, its derivative. So you need to, in finishing your problem, figure out, is this thing positive or negative at the point in question, at the price point for the skateboard. And that tells you whether to raise the price of the skateboards or not. You want it to be positive if you want to raise the price of the skateboards to get more revenue. Okay? So make sure you do that on that last grade. See you on Monday.